computer science. We are going to do some graph algorithms and graph concepts. I'm going to start with this graph, which is one of the example graphs in one of our homework assignments. Here we have it, and we're going to say some stuff about this. All right, let's start off just saying a few things about this graph. Okay, so this is a undirected graph. That's true. It's an unweighted graph. It's also true. There's no weights or numbers on the edges saying how much they're worth. All right. The vertex set is 1, 2, 3, 4, 5, 6, 7. That is the set of edges. Those are the labels that we're using. That's how we're identifying the edges. The edge set that we have here are the pairs of edges. So we have an edge from between 1 and 2, between 1 and 7, between 1 and 3, and so on. Those are the edges. We could represent this graph in terms of an adjacency matrix or an adjacency list. So an adjacency list might look something like this. One is adjacent to 2, 3, 7. 2 is adjacent to 1, 3, 7. 3 is adjacent to 1, 2, 4, 5, 6, and so on. That's what adjacency list might look like, depending on how you specify it. An adjacency matrix for this. So an adjacency matrix, we would have 1, 2, 3, 4, 5, 6, 7 on column labels, and 1, 2, 3, 4, 5, 6, 7 on row labels. Since this is an unweighted graph, we'll just put a 0 or 1 if there's an edge, yes or no. For 1, there's no edge to 1. There is an edge to 2. There is an edge to 3. There isn't to 4, or 5, or 6, but there is to 7. For 2, we already have listed up here, there's an edge to 1, 3, and 7. Something like that. 3 goes to 1, 2, 1, 2, not 3, 4, and not 7. Okay, and then we would have the rest of the entries there. Let's see, other terms, we write the degree, so the degree of, say, vertex 1, we write that as Z1 is the number of neighbors of 1, so how many edges are there coming out of 1? 1, 2, 3. Okay, so the degree there is 3. Question for you, what is the highest degree in this graph? So pause, look at the graph, what's the highest degree? The highest degree, let's see, there's vertex 3 has 1, 2, 3, 4, 5 vertices, 5 edges. 6 has 1, 2, 3, 4. So vertex 3 is going to be the highest. Degree of 3 is 5. And we can say is with an equal sign. The lowest degree, so which one is connected the least? It looks like all of them have at least 3 neighbors. All right, let's go ahead and do one of our algorithms now. We'll start with breadth first search, and I'll keep track of some things over here. So the way breadth first search is you start somewhere. Just for variety, we'll start at vertex 6. And the idea is we want to start at vertex 6 and explore the rest of the graph. See how many edges does it take to get to different things. And so we'll keep 2 lists. So for various information we're going to keep track of here. So we're going to have already explored and a frontier and some distances, which is sometimes written with just a D. So we'll have distance from 6 to each vertex. We start with 1, 2, 3, 4, 5, 6, and 7. All right, we'll initialize things. Let's say there's a distance, and we'll also say, I'll keep 2 things here. B from 6, and also parent. All right, so initially we're going to start from vertex 6. We'll say that the distance from 6 to itself is 0, and we just started from itself. The rest of these we'll leave as some kind of infinity. Meaning we haven't found any way to get there, and there's no parent. So we'll just leave the parent empty. We're going to start exploring from vertex 6. So we would initialize by having 6 on the frontier. And the rule is, for BFS, we take something off the frontier, and we look at its neighbors. So I'm going to go ahead and circle 6 here to say that we took that off the frontier. That means it's going to be in the explored. We've already done 6. And we put its neighbors on the frontier, and we put them in some order. I'll put them in, let's see, increasing order from their number. So 4, 5, 3, 4, 5, and 7. And 6 comes off. Okay, then we're done with 6. All right, now the rule is we take something off the frontier, and I'm going to keep track of the oldest things are going to be at the front, and I'm going to add on to the end here. So I'm going to take something off. 3 I'm going to take off, put it onto the explored, and when I do that, I'm going to circle it. I'm going to remember that I got there from 6. And what was the distance? So the distance from 3 to 6, I started at 6, the distance to 6 was 0, and now I've gone 1 more. So the distance to 3 is 1, and the parent is 6. I'm going to write out 6 just as to see the difference here. The first thing is the distance, the second thing is the parent. All right, and now I want to take the neighbors of 3 and put them onto my frontier, things that I need to explore. So 1, 2, I don't put 6 on because I'm already done with 6, 4, and 5. Or if I want to, I could add it on, but then later on I'll see that I'm already done with that. Just leave it like that, and now 3 is done. All right, now we take the next item off the frontier. That's going to be 4. We're going to circle 4. And we'll remember that we got there from 6. Okay, and we want to add the neighbors of 4 onto the frontier. Okay, so the neighbors of 4 are 3, 5, and 6. And the distance to 4 is 1. Its parent is 6. We should update these other ones as we put them onto the frontier. So 5, we should have updated that after we put it onto the frontier from 6, we had a distance of 1 at that point. It's not necessarily, we're not finished with it yet, but that's something we've discovered. So we have 3, 5, 4, and also this 7. We had a distance of 1 from 6. 2 and 1 we haven't seen yet. Okay, so that's what it looks like. We're done with 4 now. And we put 6 on. All right. Next thing to do is take 1 off of the frontier, put it onto the list that we're already done with, and check its neighbors. So if we look at the neighbors of 5, we've got 3, 6, and 4. We check, let's look at 3. So we could get to 3 through 5. So we could go this way, 6 to 5 to 3, but we already have a way to get to 3 that's better. So we don't do anything with 3 because of 5. So as we put 5 on here, you can think of adding these on, but they're not going to change anything because those are already done being explored. So let's leave those off. And the next vertex to take off is 7. So 7 is going to be taken off of frontier and put into explored. I'm going to mark it as something we got to. And draw the path that we had was from 6. And now we're going to look at 7's neighbors. 7's going to go over there, and 7, we look at the neighbors. Now 7 has a path to 1 and 2. So if we look at 1, we can get to 1 from 7, 6, and then 7, and then 1. We already have one distance, one edge to get to 7, and another edge to get to 1. So this is going to be distance 2 from 7, and same for 2. Vertex 2 is distance 2 from 7. And if we wanted to draw those paths, we could. We already know that path is there. All right, what happens next is we take 1 off of the frontier, put it onto the explored set, and I'll mark it as explored. And we would look at all the neighbors of 1. We could get back to 7, but that would be with a longer distance. If we go 6, 7, 1, 7, that's longer than 1 there. We could get to 2, 6, 7, 1, 2, but we already have a path of length 2 that's better. So that would be it for 1. None of this information gets updated. And then we would take 2 off of the frontier. none of the information gets updated with 2 either. And that's the end. All the rest of these that were on our frontier, we have already finished exploring. And so this would be the end. We have the distance from 6 to each of these vertices, and we have paths to each one. So we get from 6, we need to write in this to 5 as well. We did finish 5 in there. As well. Okay, so what we've done is we've gotten paths from 6 to each of the other vertices. Okay, so that's BFS, and the basic idea there, it's in our notes over here, is you start with where you're starting. You always keep track of the frontier that you need to explore, and you take the oldest items off the frontier to explore next. And what that ends up making happen is you explore the vertices that are closest to where you started first, and you end up getting shortest paths in terms of the number of edges from where you started to each other vertex in the tree, in the graph. Okay, let's contrast this with, we're going to do depth first search, DFS. So we're going to do a DFS. Starting from 6, we'll have an explored. The oldest is first, but in DFS, we take off from frontier most recent. And BFS, we take off from frontier oldest. So here we'll have not distances, but percent of each. So this is going to start off 1, 2, 3, 4, 5, 6, 7. All of these will be initially nothing, except we'll keep track of, we've already seen 6. And I'm going to highlight this with some other we'll do rectangles. Okay, so the rectangle will represent our progress in the DFS. We start off with just 6, which is, so we start with our frontier like that. We're going to look at all the neighbors. We'll put them in increasing number by the number, 3, 4, 5, 7. And then we take 6 and it's on our explored list. For the next step, we take a vertex from the frontier, put it onto explored, and we'll take the most recent. So the end of this list is going to be 7. Alright, so we're going to mark that we've done 7. And we want to put a mark there for the path. And 6 is the parent of 7. That's the same as the BFS, so we do have that same edge there. All right, and we put the neighbors of 7 onto the frontier, 1, 2, and we'll leave 6 off because we've already explored 6. All right, now we see where the difference is. With the BFS, we ended up exploring the closest edges to 6. Now we're taking off of the newest. So the most recent thing we put on to the frontier was 2. So now we're going to take 2 off. We'll put our rectangle around it. And we got there from 7. Okay, so we get to 2 from 7. We should also make a note that from 7 we got to 1. When we put something on the frontier, we need to keep track of that. All right, and then 2 is going to be off the frontier and any other neighbors of 2. So okay, here we are. We are at 2, and we add the neighbors of 2 onto the frontier. That's 1 and 3. They're already there. So that's it for 2. We've got 1 as the parent of 7. 3 should have also been, let's see, 3 should have been parent being 6, because it was a neighbor of 6 that we initially put on. 4 should have been a neighbor of 6. 5 should have been a neighbor of 6. Sorry, a parent being 6 there. Okay, so that would actually be it. We have parents for everything, but if we kept going like this to see what path we're going on, we were at 2. We take off the next thing from the frontier. That would be 1. 1 would be explored. So if we mark it as explored, we got there through 2. This way. 1's neighbors already have been explored or are on the frontier. But we would have put on the 1's neighbors would be 2 and 7. They're already done. We'd have 3. If we put that on again, so we would have this path here going to 3. And 3 would be done. Neighbors of 3, we have 4 and 5. Those are already on the list, but if we put them on as something coming from 3, then we would have reached 5 here from 3. And then we have neighbors of 5. 5 goes on to the explored list. Neighbors of 5. Things that aren't actually explored yet would be 4. So we have 4 that we reached from 5. All right, and then if we traced through what we actually had there in terms of this route, what did we have? We started at 6. 6 is a parent of itself. When we took 7 off and put it onto the explored list, its parent was 6. We took 2 off and put it onto the explored list from 7. So 2's parent would be 7. We're drawing the path like this. And then we went to 1 from 2. And from 1 we went to 3. From 3 we went to 5. And from 5 we went to 4. Alright, so this is the path that we traced off by taking off the frontier the most recent. Okay, so we start with 6. Its neighbors get all added to the frontier. We pick one of them to explore first. We go this way. We forget, so we're not looking at the neighbors that we had already added for 6. They're in there, but we go the most recent first. So we keep taking a path deeper this way. This is called depth first. We keep taking a path as deeply away as far away from 6 as we can before we would ever trace our way back. So we keep going along, most recently added, until we can't go any further, and we've covered this whole graph. All right, so there we have DFS and BFS. With BFS, we're doing the oldest first, the closest to the source first. With depth first search, we're doing the most recent first, which means we're going as far away as possible from the place we started first. And you can see, if you pause, you can look at the dark black path that we traced versus the dark green path. Some other terms that we can throw out that we can just review. Okay, so this graph is connected. That means from any vertex you can get to any other vertex. This dark green is a tree. Tree means there are no loops. The original graph is not a tree. You could go from 7 to 6 to 3 to 2 back to 7. So there's a loop there called a cycle. A tree has no cycles. All right, so those are all words that we're supposed to know. Let's review terms. We'll put highlighted ones that we still need to talk about. So what is a complete graph? Shortest path. We need to say something about that. We still need to do Dijkstra's algorithm and Prim's algorithm. I think we'll do another video for that. Some other terms. Bipartite graph. Say something about that. And we're halfway there to the stuff we're supposed to know about graphs. Okay, we'll stop there for this video. We'll do another video with more graph stuff. So this will be graphs part 1.